So this is a little bit of a, this is going to seem a lot like a blast from the past. It's got a lot to do with advanced functions. So we're going to look at polynomial and rational functions. Polynomial functions, it's a cinch, basically, because they're continuous everywhere. We don't have to worry about it. If it's a rational function, on the other hand, we'll have to do that thing where we factor the top and factor the bottom, and then see if there's that removable discontinuity or a hole, or if there's an infinite discontinuity. There's a third sort of example where there's an absolute value function, and it's a kind of an interesting example. Theoretically not on the curriculum, but we can take a look at it. Okay, so we're going to look at taking the limit of this quadratic function as x approaches, oh, not a, but 3. Anyways, it's a quadratic function. They're continuous for all real numbers. We have nothing to be afraid of. So basically, all we really have to do is plunk the 3 in for x, and we can evaluate this limit. We know the limit from the left is going to equal the limit from the right. And even though we don't have to worry about it, even the function exists at this point. 9 plus 9 is 18, it's 20. And so there we go. It's a polynomial function. It exists everywhere. We have nothing to fear. All we have to do is put the value of x in, and we can evaluate the limit. Okay, so if we approach this, if we approach 3, we would find that function has a y value. The graph of the function has a y value of 20. Does that make sense? Perfect sense. Okay, here we are. All right, so here we have a rational function. It's a second degree denominator, it's a first degree numerator. And this is that situation where you can see this has 2 probable discontinuities. X can't be equal to 3, and x cannot be equal to -1. But these are 2 distinctly different kinds of discontinuities. So if you recall, this is the removable discontinuity, and so we can simplify this. We can express this function this way, as long as we're mentioning the fact that x can't be equal to 3 and x can't be equal to -1. The fact that we're using a limit means that we're not actually putting the value of 3 in. We're just looking at the function on either side of 3 and seeing what that value is. And so if we put it in, we can actually see that this is equal to 1 over 3 plus 1, that the function exists. Okay, it's a removable discontinuity. All we really have to do, usually, is factor the top and factor the bottom. Make sure we've figured out whether we've got the removable discontinuity or the infinite discontinuity. If I take exactly the same equation and I look at x approaching -1, wow, suddenly everything changes. Oops, I'm going to have to change the limit as well. When I say everything changes, I mean not very much changes, so that I don't have to change very much at the board. There we go. So if I put the value of -1 in for x and hope for the best, it's going to be bad. Okay, I'm going to get the 1 over 0 condition. So if I approach -1 from the left, so for example, I put in a -1.1, I'm going to get a big negative number. And if I approach from the right, so I approach from above, approach -1 from above, in other words, -0.9, -0.99, I'm going to get a large positive number. And of course, that is not a surprise because we know that the simplified version of this function is really just one of those rectangular hyperbolas. Okay, so it looks kind of like that. Uh-oh. And what did we say? X couldn't be equal to +3, -3?
+3.
+3.
-1.
Okay, there we go. So there we have the whole there. Oh my goodness. There we are. There we have an asymptote there. Okay. So this, the limit does not exist as x approaches -1. And we know that because the limit from the left is not equal to the limit from the right. Not only that, really, infinity is not a value for a function. So even if these were both positive or both negative infinity, the limit would still not exist. Okay, let's look at an example. Let's look at an example where we can factor the top and the bottom. Limit as x approaches -1. X squared minus 1, and let's do there we go. So super simple. So this is that case where, yes, we can factor the top and factor the bottom. Maybe I made it a little bit too easy. The top is the sum of squares, the bottom is the difference of squares. Okay, we can factor it. Yes, we definitely have a removable discontinuity there. We have an infinite discontinuity here. Since I've fixed this up, I can now put in my limit. And just making sure, oh yeah, x can't be equal to -1. X also can't be equal to +1. So now I'm ready to put in my limit. I'm just going to put in -1 for x. Lo and behold, the limit is 0. So 0 is a perfectly legitimate value for a function, for the limiting value for a function. Ready? Last kind. This kind, technically, we are a little bit through the looking glass here. This is technically not on your curriculum. This is a limit that involves an absolute value function. Okay, so this is the absolute value of x minus 3 being divided by x minus 3. And actually, this is kind of a neat function to put into Desmos, because you're going to see that this actually ends up with a jump discontinuity when x equals 3. So it flips from, having a value of -1 to having a value of +1 just as x goes to 3. And so this is one of those cases where it looks kind of like the top and bottom would cancel out, right? And you'd be going, oh yeah, the top's going to cancel with the bottom. Everything's going to be golden, which is kind of true. But the problem with it is, even though that is kind of true, the limit from the left is not going to be equal to the limit from the right. Now we can think of the absolute value function as being a two-part function. Okay, so this is just going to be x minus 3. It's just the function x minus 3 as long as x is greater than 3. Okay, so if it's 4 minus 3, this value is 1. The absolute value hasn't changed, x minus 3. So as long as x is greater than 3, it's just the function x minus 3. On the other hand, if x is less than 3, so if the x was 2, for example, 2 minus 3 is -1. And the absolute value makes it 1. And so really what it's done is it's flipped the sign. And so this becomes -x plus 3 whenever x is less than 3. So the function subtly changes as we come around to this value of 3. Okay, so let's look at the limit as x approaches 3 from below. And so we're going to be approaching 3 from below, and so this is our function from below. Okay, so I've just substituted this value from the piecewise function up here. I'm approaching 3 from below, and this actually cancels out to be equal to -1. Now let's see what happens when we approach 3 from above. In other words, this is the case up here. X is greater than 3. Well, this is just x minus 3 over x minus 3. So this is equal to 1. And so what we have, basically, even though this looks like a nice function, as x approaches 3, this has a jump discontinuity. It's -1 as we approach from below or from the left. And it's +1 as we approach from the right. And so the limit of the function as x approaches 3 from below is not equal to the limit as x approaches 3 from above. And so the limit does not exist. It fails to meet that criteria of approaching from above and below. So that's it. If you've got a rational function, make sure you factor it. If you've got a polynomial function, just throw the value of x in you will be fine, okay? Same thing with an exponential function. A couple of weird ones. If you've got a rational function, you might have a removable discontinuity. You might have asymptotes, in which case the function heads off for infinity, and the limit won't exist. And that's about it.